The talk I will present will be a sort of an overview about the moment LP and moment SOS approaches. And I decided to do this talk because I know that in the audience there are some people who are not really aware of this methodology. I know many of you already knows most of what I'm saying, but I decided to present this because of some people in the audience really don't know much about it. And maybe a few things at the end will be new. So our first one slide about what is semi-definite programming, which for us would be just a black box that we use for all the purposes. Then I will talk about why we speak about polynomial optimization. Then I will go to LP and SDP certificates of positivity, which yield what we call the moment LP and moment SOS approaches. And I will end up with two examples outside optimization, where we can use this methodology for approximating sets defined with quantifiers, and also to provide a means of computing polynomial convex polynomial underestimators, which are very useful for mixed integer nonlinear programming problems. So semi-definite programming, just one slide to remind people what is a semi-definite programming problem. Well, it's very easy. It's just a finite dimensional optimization problem. So we are in Rn. Everything in blue is the data. Everything in red is what we look for, the unknown. So an SDP just solving, you want to minimize a linear functional. Jesus. Yeah. C prime of x. And you make a linear combination, the constraints of the x variables are just that you make a linear combination of some given matrices AI, which are real symmetric. You subtract the matrix B, which is given and real symmetric, and the result should be a positive semi-definite matrices. So the only x you consider are those who satisfy those constraints, and you want the one that minimize C prime x. And this is the standard notation, as I say, the standard notation of positivity means that the resulting real symmetric matrix would be positive semi-definite. So just an example to tell you what it is. For example, 2 by 2 matrix with linear entries, x1, x2, that would be an SDP. And it has a dual problem, what we call P star, as all convex problems have, which are solvable. What we have to remember that an SDP, its main feature is that it's solvable in time polynomial to arbitrary precision, epsilon positive, fixed in advance. And it's a generalization to the cone of linear. It's a generalization, sorry, of linear programming to the cone of positive semi-definite matrices, because when you have diagonal matrices, in the particular case of diagonal matrices, you are just solving a linear programming problem. And there are, of course, several academic SDP software packages, like the MATLAB LMI Toolbox, Sedumi, SDPT3, and so on. But the problem is that so far, the size limitation is much more severe than for LP software packages. And the pioneer contribution in the field are coming from the Russian school of Dmirovsky, Nesterov, Shor, Yudin, all these brilliant people. So I won't say anything more about SDP, but just remember that when you have to solve an SDP, in principle, you can do it efficiently, and that's what we use in the methodology that we describe later on. So now I come to the main topic. It's why polynomial optimization. So what is an polynomial optimization problem? It's just a finite dimensional optimization problem where you want to minimize a function f, which is a polynomial, subject to finitely many constraints, inequality constraints that are defined by polynomials. So in fact, if you see the problem like this, you say, why polynomial optimization? Because after all, it's just a case of nonlinear programming, right? And there have been books, and there's a complete theory about optimization with convex, non-convex problem. But this is true only if you are interested in a local optimum only. Of course, if you just want to find a local optimum, there is no need to have a special theory for polynomial optimization. It doesn't help. All the tools that we already have are enough. But when you search now for, And as I say, when you search for local minimum, optimality condition and descent algorithm use basic tool from real and convex analysis and linear algebra, and that's basically enough. But the focus in this case is about how to improve your criterion at the point x by looking at a local neighborhood of some nominal point. So you have an iterate x belongs to k, and you want to improve locally around x at the criterion, and you proceed by local improvements. But in general, you cannot infer any global property of the points you end up with, right? And the fact that f and g are polynomials doesn't help much when you use this kind of methodology. It's just a function like another one. If you use the gradient, Hessian, and so on, and you move locally around that point, and the fact that you are handling polynomials, well, it's not so special, right? Now, if you think about global optimization, the picture is different. Because remember that in global optimization, a rephrasing of the problem is that you want to compute f star, which is just like you want to maximize lambda, so that f minus lambda is non-negative over for all x belongs to k. So this is just a rephrasing of your problem. But it's very important because it tells you that the global minimum, this is one characterization of the global minimum, which is not valid for a local minimum. This is only true for the global minimum. But if you would, and what makes it complicated, that if you want to compute f star, then you need tractable certificates of positivity on k. You need to be able to handle this constraint that says that f of x minus lambda should be non-negative for all x in k. And of course, even if f would not be a polynomial and k would not be a semi-algebraic set, this would be very extremely difficult. That's why you don't know how to do it. And the message is that if you are restricted to the case where f is a polynomial and k is a compact basic semi-algebraic set, then you can do something more than in the general case. And in fact, in this framework, real algebraic geometry helps, because you indeed can provide powerful certificates of positives that exist. But not only that, and even more importantly, maybe, that such certificates are amenable to practical computation. Because, for example, we will see a positive certificate by Putinar in particular, but such a positive certificate exists for a larger class of functions. For example, for analytic functions, you have the same kind of positivity certificate, but you don't know how to use it. So it's not enough. In mathematics, sometimes people are satisfied with a nice mathematical statement, but the magic behind these positivity certificates of real algebraic geometry is that not only they are very powerful in terms of theory, it's a very elegant, simple statement, but also you can use it practically. So, of course, you understand always that in mathematics, you always want to be as general as possible. This is one direction in pure mathematics. So, for example, some people would find that the same positivity certificate for analytic function is even more interesting because you address a larger class of problems, right? But at the same time, you don't know how to use it for practical computation. So, in my mind, this positivity certificate of Schmudgen, Putinar, and others have this magic that not only they are very nice because they address a sufficiently large class of problems, but at the same time, you can use it efficiently for doing practical computation. And that's what I think is the difference in this case between pure mathematics and applied mathematics. Well, for example, what is such a certificate? Well, we have one which is SOS-based, sum of square-based certificate. And what I like in this certificate, and every time I present this result by Putinar and Schmudgen, I warn the audience, especially if they don't know this field, that it's, for me, at least, it's one of the few results in mathematics which is easily understood by a freshman at university. The statement is very easy to understand, and still it has a lot of application in many fields. And I don't think this is very frequent in mathematics, that you have a nice statement that everybody can understand, and still is very easy to use for a lot of applications, and it proves to be efficient. So this is one such result. It's called Putinar positive Selensat. I'm guessing that in a few years it will be a standard result. It says the following thing, which is kind of relatively easy. So you have a compact set K, which is a basic semi-algebraic set, meaning that you have a set defined by finitely many inequalities defined by polynomials. This is a set K above. Plus a technical assumption, which is called Archimedean assumption. So I don't speak about that because it's not very important in terms of restrictions. And so, provided you have this slight technical Archimedean assumption, then it says the following. If f is a strictly positive polynomial on K, then you have a certain way to write f, to represent f, in terms of a weighted sum of square of the GJ that define the set K. So in other words, you can write f as what? As a polynomial sigma 0 of x, which is a sum of square, plus a linear combination of the GJ that define the set K, and the weight in front of each GJ is a sum of square sigma j. Sorry. Yeah. All right. And of course, you see immediately that when a polynomial f can be written this way, you immediately see that it is positive on K. You don't need to check, because the simple fact that you write it this way and you take a point x in K and you evaluate f of x, you immediately see that it is non-negative, right? So it's a nice certificate, of course. And the hard part of the result is to prove that every positive polynomial can be written this way. So that's the mathematical statement, right? Easy to understand, very, very easy. And the additional feature that I mentioned before is that if you want to test whether this condition holds, and of course, if you want to test it practically, so for example, you say f could be a polynomial of degree 2, but then to get this representation, you might have to go to degree 10,000, for example, for the sigma j. But if you fix a bound a priori on the sigma 0, sigma j, then testing whether this is true is just solving an SDP. So that tells you that to check such a condition, you can do it efficiently by solving semi-definite programming problems. All right, this is one such certificate. Another one, which is based now on linear programming, still the same set K, but now you assume that the GJ are normalized so that the GJ are between 0 and 1 on K, and that the family of GJ is rich enough to generate the whole algebra of polynomials. So provided you have those conditions, then if a polynomial f is strictly positive on K, now you have another way of represent f, not as before, but now it's a different way of representing f. Now you can say that f is also a certain weighted combination of the DJ, but not now only of the DJ, but all powers of DJ and 1 minus DJ. So you see the difference between the one we had before. Here, the DJ, you have a representation which is linear in the DJ, and the weight is a polynomial. So there is some complexity in the weight. Now, in the LP representation, the weights are extremely simple. There are non-negative weights, scalars, but now the complexity is in the power of the DJ. So you multiply the DJ between themselves, right? And of course, when you see a polynomial written in this form, again, it's immediate that this polynomial is positive on K, because when you evaluate x in K, f of x when x is in K, you immediately see that it is non-negative, right? And again, if now I give you a polynomial f and you want to test if f can be written this way, now you have to put a bound on the sigma of alpha j and bj. But if you put an a priori bound on alpha j and gj, testing whether this condition holds is now solving an LP, sorry. So a priori, you would prefer such a representation than the SDP one, because it is known that you can solve very, very large LPs, whereas so far the state of the art for SDP is not that nice compared to the LP1. So in principle, you would prefer such a representation. But in fact, it has some drawbacks. So not all certificates are that nice. And my bias is that I think the SOS one is, there's some theoretical reason to sustain the statement that the SOS base is a better certificate. So when you have such positivity certificates that allow you to infer global properties for feasibility and optimality in an optimization problem, which are the analog of well-known previous one, but were valid only in the convex case. And this one such certificate was the Farkas lemma in linear algebra that now has a counterpart in nonlinear optimization and nonlinear systems by the Krivine-Stengel positive certificate. And for optimization, the Karish-Kuntucker optimality condition in the convex case, the property of a KKT optimality condition in the convex case, have a nice Duar analog in what I call the Schmudgen-Putinar certificates, or global optimality condition, valid for the non-convex case. So I will say a few words about that. Well, in addition to what we said about non-negative polynomials, they are ubiquitous in many, many applications. They appear in many important applications, and not only in global optimization. And as I say, I will try to finish my talk after that, after some other slides, about two instances of applications not related directly to optimization, where you can use this kind of methodology. For example, to approximate sets defined with quantifier. For example, you would have a set RF. You would like to define a nice approximation of the set of x in a box B, so that f of xy would be non-negative for all y, such that xy belongs to some set k. The other one would be same thing, but now for some y instead of for all y. And you would like to approximate this by sample sets, sub-level sets of polynomials. Also, you would like to compute convex polynomial underestimator of a polynomial f. So we'd like to provide f is a non-convex polynomial on a box B, and you would like to provide a convex polynomial underestimator relatively efficiently, which is very useful for solving large-scale mixed integer nonlinear programming problem. So what are the moment-LP and moment-SOS approaches? Well, it's very simple. It consists of using a certain type of positivity certificate, either the SOS one by Schmudgen and Putinar, or the LP one by Krivine-Stengel, in potentially any application where such a characterization is needed. So you don't need to think about polynomial optimization only, but everywhere you would have a constraint saying that some polynomial should be positive on a certain set, K, which is a basic semi-algebraic set, then you could invoke either the LP1 or the SOS1 certificate. And it would be very useful. And in many situations, this amounts to solving a hierarchy of either a linear program if you use the LP certificate, or semi-definite programs if you use the semi-definite programming certificate. Of course, the size increases in the hierarchy. So you would like to terminate very early in the hierarchy for efficiency reason. So for example, for optimization, what are the LP and SDP hierarchies? So remember that the rephrasing of what is a global optimum F star would be the same thing as finding the maximum lambda, a scalar, such that the polynomial f of x minus lambda would be non-negative on K. And you try to find the maximum lambda for which this is true. So the idea is just, the SDP hierarchy is just to say, well, you replace the f of x minus lambda non-negative on K by the positivity certificate, and you have the choice of either choosing the SOS-based one or the LP one. If you choose the SOS one, this would give you a hierarchy of SDP. You want to maximize lambda, such that f minus lambda now is just a linear combination of the DJ as in Putinar certificate. But you of course put the additional constraint that the degree of these guys is bounded in advance by some d. So you start with d equal 2, d equal 4, and for each d fixed, solving this is solving an SDP. And you know how to do it efficiently. And the idea is that you fix d, you solve this SDP, you obtain this lower bound on the global minimum, and you expect that if d is not too large, you would have a good idea of what f star is. And in fact, the good news is that with d usually very low, you get sometimes exactly the global minimum. That's the message. Or if you take the LP hierarchy, you do exactly the same thing. You replace this hard constraint, f of x minus lambda non-negative on k, which is hard to state. You replace it by this one, by this LP certificate of Krivine angle. You say that f minus lambda would be this type of combination of the GJ, while you put, again, a bound on the alpha plus beta. You don't allow alpha of beta to be as large as possible, but just you bound alpha and beta by some d, and then you increase d. So you fix d, you solve this. This is solving an LP now. Well, it's easy to see, because if you say that this polynomial is equal to this one, you expand in the monomial basis, and that will give you linear constraints on the C alpha beta, which are the unknown, right? And then it should be non-negative. It's an LP. Okay? And the theorem says that because of those Putinar certificate or Krivine-Stengel certificate, if you let D increase, either in the SOS-based hierarchy or LP-based hierarchy, if you let D increase, then you convert to a global minimum. Okay? So that's the good news. But now you have to think about efficiency of these two hierarchies. And what makes this approach exciting is that it has of course, as we said, and Monique made a nice summary of this, that this approach is exciting because it's at the crossroads of several disciplines and applications. It's indeed, it's a mixture of commutative, non-commutative, and nonlinear algebra. Real algebraic geometry and functional analysis. This is a convex duality between positive polynomials and moment problem. Then you also use some part of optimization and convex analysis, and also computational complexity in computer science. And all those areas benefit from interactions. And in addition, and as mentioned, potential applications are really endless. And I remember there was this book in 1987. It's called Moments in Mathematics. It's a IMS proceeding in symposia for pure and applied mathematics. So you have at least 10 chapters about potential application where the moment problem and of course the SOS positive polynomial duality applies, and it comes from any fields like probability, statistics, operator theory, and so on and so on. So it has already been proved useful and successful in application, but so far with modest problem size, right? Well, we are not in the paradise yet. So notably in optimization, control, robust control, optimal control, estimation, computer vision, etc. It has initiated and simulated new research issues in convex algebraic geometry, like semidefinite representation of convex sets, algebraic degree of semidefinite reprogramming and polynomial optimization. Also in computational algebra, for example, for solving polynomial equations via SDP and border basis, which complement classical algebraic techniques. And also in computational complexity, as mentioned also Monique earlier, that LP and SDP hierarchy have become an important tool to analyze hardness of approximations for 0-1 combinatorial optimization problems. And also establish links with quantum computing, using non-commutative version of this. But I would like to mention now a remarkable property of the SOS hierarchy compared to the LP hierarchy. So it's a property that is not shared by the LP hierarchy. It's really proper to the SOS hierarchy. Well, this first property is common to both, actually. It says the following. So when you're solving an optimization problem of this form, with this framework I just mentioned, the way you describe your set K, GG of x non-negative, think about this. You can have, at the same time, nice convex sets or completely disconnected set, eventually with some discrete parts, right? But in the description of your set, you don't care. You just don't pay attention to the fact that your set is potentially discrete or convex or disconnected and so on. For example, if you have a Boolean variable, you would just model this constraint by a polynomial equality saying that xi squared is equal to xi, right? Which is completely orthogonal to what you do in nonlinear optimization, right? In nonlinear programming, if you have a constraint of this form, and you describe your constraint like this, and then you say, okay, now I have my toolbox of descent algorithm. If you would use a descent algorithm with such a constraint, people would laugh at you because they would tell you immediately that this is not a good way of solving your problem. They would tell you, this is a discrete problem. Don't use the descent algorithm. Rather use these kind of methods, right? In fact, the methodology in nonlinear programming is to have a ad hoc Taylor algorithm for each class of problems. So if you have a discrete problem, you have a certain class of algorithm. If you have a convex one, you have a certain toolbox for those convex problems. If you have a continuous and non-convex problem, then you have other methods also, right? Here, the way you describe the problem, you don't pay attention to any of these particular feature of your problem. You just describe your set. So immediately when people tell you, if you have a general methodology, while you don't pay attention to the particularity of your problem, probably this is not a good idea. Because you lack specialization. And in the practice of nonlinear programming, that's really what people tell you. They don't believe in a general tool. Say, if you have a discrete problem, use this. If you have a convex one, use this. If you have a non-convex one, use rather this kind of method, and so on, right? And the magic between the SOS relaxation has the following feature, that even though the moment-SOS approach does not specialize, an S here should disappear, to each class of problems, then it still recognizes the class of so-called easy SOS convex problem. So even if you don't tell the program that your problem is modeled by SOS convex polynomial, so it's a certain class of problems, right? But you don't know in advance, it will recognize it and will solve your SDP. Your first relaxation will be exact. So you stop immediately, right? Good news. And this is not true for the LP hierarchy. Very important. But in the same time, if you apply the same methodology, using this naive way of representing a discrete variable by xi squared equal xi, right? Just put that in the description of your problem, then it would still provide the best approximation among all methods that give lower bounds for your combinatorial optimization problem. So I think this is really nice, and this is not very common for general methodology. So I'm not claiming that it is the best way to solve each class of problems, but at least for an easy problem, if you have an easy problem and you input this easy problem into your general solver, it recognizes it. And I think this is a very nice feature, and for me, this is a sign of the strength of this Putinar representation. That is not true for the Krivine-Stengel representation. Actually, if you think about complexity theory, and you would compare, especially now when you look at this LP and SDP hierarchy for combinatorial optimization problem, they try to see, to evaluate the hardness of approximation by applying this LP SDP hierarchy and see what is the best one, or how good are the lower bounds. But they never look at the problem that I give you a general methodology, right? In principle, you can solve easy and difficult problems, right? But for me, if I had to buy a package, suppose someone is selling me a package that pretends to solve hard problems. If I had to pay a lot of money for this package, the first thing I would do is what? I would try to see how it behaves for easy problems, right? Because suppose this hierarchy is very bad for easy problems. Would you buy it for solving harder problems? I would not. If I pay, if it's cheap, it's okay, right? But if it is not cheap, I will not buy a package that behaves already very badly for convex problem. And in fact, what is very annoying in the LP hierarchy is that it cannot be exact for a convex problem. So if I give you a convex, except for linear programming, if I give you a convex problem and you apply the LP hierarchy, the convergence is only asymptotic. It cannot be finite. So for me, this is really annoying. But in complexity theory, people don't care about this kind of arguments, but I think it should be one. Not the only one, but it should be an argument also. another remarkable property, which has nothing to do with convexity, is that the finite convergence of the SOS hierarchy is generic. So that it provides a global optimality certificate in almost all cases, meaning that the SDP hierarchy eventually stops, except for very degenerate problems. And this is exactly the analog for non-convex case, of what the KKT optimality condition do in the convex case. And this is a result by Marshall and Lee. Let's say the following. So suppose that X star is a global minimizer of your optimization problem, right? And now you take the standard, almost standard conditions that you have, constraint qualification that you have in nonlinear programming. That, for example, the gradients at the point X star are linearly independent, strict complementarity holds, and second order sufficiency condition holds. In all NLP books, you find those conditions for establishing the Karush-Kuntuker optimality conditions, right? But here, for the same condition for the global minimizer, then it tells you that then you have Putinar representation, right? And not only that, all these conditions 1, 2, 3, all generically. So it means that except on a negligible sets of data, where the data would be the F and the DJ. So if you fix, for example, the class of problems you want to solve, M constraints of degree at most D, for example, and F is of degree at most D, then the data for which this problem will not be solvable, like this, is a set of measure 0 in the space of coefficients of F and DJ, which I think is a nice result, even for the genericity in the case of KKT optimality condition. So this result by Marshall in 2008 was refined by Ni 2 years ago. In summary, so what you have to make the analog between KKT optimality condition in the convex case, I insist on that, and Putinar representation in the non-convex case, where in KKT optimality for the convex case, what you have is that if F and GJ, so F and minus GJ are convex, then a global minimum, a local minimum would be a global minimum. Then you would have, of course, the gradient of F is a linear combination of the gradient of GJ. And you have that the Lagrangian F of X minus F star minus sigma of lambda J GJ, which is called the Lagrangian, is non-negative on the whole space. And X star is a global minimum of the Lagrangian. But this is true only for the convex case. In a non-convex case, you would have still that delta F, the gradient is linear combination of the gradient of GJ, but that's all. It will be just a stationary point of the Lagrangian. Only in the convex case, X star is also a global minimum of the Lagrangian. Okay? Now, if you look at Putinar certificates, which we have seen by Marshall and Lee theorem all generically, so you would have, again, that you have this gradient equality, that the delta F is a linear combination, but now you see the weight is a polynomial, and only at X star it's a scalar, of course, and this is a lambda that you have here, the same lambda. But now it will be not a scalar, it will be the value at X star of the SOS weight. And now the good news is that F of X minus F star, minus sigma of, so it's a sort of generalized Lagrangian, now with weights which are polynomials, is also non-negative on the whole space because it's a sum of square. And X star is a global minimum of this extended Lagrangian. So in other words, you see, you have exactly the same property in Putinar representation in the non-convex case, the same properties that you had with KKT condition in the convex case. So it's really the extension to the non-convex case of KKT in the convex case. And of course, you don't have this for the LP relaxation in general. So now I don't know if I have how much time? Yeah. Yeah. I will say rapidly how to two examples of application outside optimization of this LP and SOS hierarchy in this case. So suppose you would like to approximate, you have a set K that depends on two sets of variables, X and Y, call Y, for example, a parameter. So we'd have to So K is a basic semi-algebraic set defined like this, right? B, for example, is a unit ball that contains K. It's just a normalization to have the box minus 1, 1. And suppose you have a set like this. So you want to find the set of x in B so that f of x, y is less than 0, let's say, for all y such that x, y belongs to K. So you would like to approximate this set with a sample set. You would like to eliminate y and have a representation of the set Rf like the sub-level set of a polynomial. Okay? So you would like to approximate this guy here by a guy of this form, and you would like the approximation to be good, of course. So you know, of course, by Stone-Weierstrass, everything is compact. So by Stone-Weierstrass, you know that such a guy exists, but you would like to compute it efficiently. How do you do that? Well, you define, remember this is the quadratic module, so the set of polynomials is a sort of certificate of positivity on K, right? The polynomial that you can write in this form. So you look at this function f, which is a max. Remember, you want to find f so that f of x0 is less than 0. So you would like the max with respect to y of this polynomial should be non-negative, right? So you define this function f, which is the max of f of xy. For each x fixed, this would be the maximum of fxy when xy belongs to K. And then you look at this optimization problem. Now you look for a polynomial g of a certain degree, so you fix K, and now you are looking for a polynomial of degree at most K, call it J, so that you minimize the discrepancy between G and F. So G would be greater than F, because you write that G is a overestimator of F, let's say. So you want to G of x minus f of xy greater than 0 when x belongs to K, xy belongs to K. Right? And then so this quantity is always non-negative on the box. And you want to minimize this. So it would be, sorry, the box here. Sorry. So this quantity is just a constant term that you don't know f, of course, but this is a constant term, so you don't care. Now you have plus sigma of g alpha. G is a polynomial. And this is easy to compute because these are the moment of the Lebesgue measure on B. So now you have a linear combination of the coefficient of G, right? And the constraint that this is non-negative is just a Putinar certificate. And this will be the GG of the box, sorry. Okay. So this SDP, this is an SDP. When you fix the degree, a priori degree K, this is an SDP. And it has an optimal solution. And of course, if you do the LP-based certificate, you would have an LP instead of an SDP. And from the definition of GK, this sublevel set is an inner approximation. So when you compute this GK, and then you look at this set, it's an inner approximation of RF. And what is nice is that you get not only you get convergence in a strong sense, in the sense that the L1 norm of the difference, because this is always greater than f, goes to 0. And of course, if this function f is a 0 set of fx as Lebesgue measure 0, then the volume of the difference between your set that you don't know how to represent and this one, which is a sublevel set of the polynomial gk, the volume of the difference, the Lebesgue volume, is going to 0. So you approximate it in a nice way. So it's an example that we did with Didier about robust control. For example, you suppose you have a nonlinear matrix inequality. Okay, so your set RA now is a set of x in a box. So that is polynomial matrix inequality, which is nonlinear. So A of x is a matrix, right? Each A alpha is a really symmetric matrix. So you take a polynomial combination of the A alpha, and you would like to look at the set of x for which this polynomial matrix, is positive semi-definite. In other words, you want to find the set of x such that the minimum eigenvalue of A of x is positive, right? Well, you just rewrite that this RA the same as you want to find the set of x in B, so that this polynomial is non-negative for all y belongs to this. Right? So for example, to give you an example of how it works, so here you have this nonlinear matrix inequality. You apply this methodology, so you solve a sort of a hierarchy of SDP, which are relatively simple to define. And then for each k in the hierarchy, you obtain a polynomial theta k and an associated sublevel set. And then you have this difference. And just to tell you just an example, so this the set that you want to approximate in this case is this non-convex set in gray. And with theta equal 2, so when you look for a quadratic, an ellipsoid, so this is the first approximation in a hierarchy. You approximate it with an ellipsoid from inside. With k equal 4, now you have a quartic. So this is the shapes start to mimic the one of the set you would like to approximate. If you go to degree 6 and degree 8, this is what to obtain. So it's after the 4 iteration. And you see the sublevel set of your polynomial is mimicking the shape of your initial set. Okay? And you can do exactly the same thing for a set which is now defined like f of x less y less 0 for some y now instead of for all y. So it's like you look for the projection, a sort of a projection. Right? And again, you can approximate this by a level set, but now you will look at the minimum of f of x y. This is the same thing as saying that the minimum of f of x y when x is fixed should be less than 0. And then you would have a hierarchy of outer approximation doing exactly the same thing, sort of symmetry here. And that's the way it works. So I don't go details. And I end up with it's just a convex underestimator. So suppose now in large-scale mixed integer nonlinear programming, mean LP problems, a popular method, when you suppose it's a large-scale problem, so we cannot use the SDP hierarchy to pretend to solve this problem because the size would be too large. So what people do in general is they try to do to combine a branch and bound method with at each node in the tree, in the search tree, you want to have good lower bounds to make your branch and bound efficient. So how do you find a lower bound when your problem is non-convex, nonlinear, discrete variables? One way is to build up convex underestimator. So then you minimize f, which is non-convex. You provide a convex underestimator of f, and then you compute the lower bound with this convex underestimator. Because you have a convex problem to solve, you can do it efficiently, right? And the deal is, of course, the efficiency of your approach depends on how good is your convex underestimator. So how do you compute a convex underestimator? Then the message is that using the above methodology, you can compute good convex underestimator by using this Putinar certificate. So what do you want to do? It's very simple. So suppose f is your polynomial which is non-convex on the box B. Well, you look for a polynomial P that will be dominated by f on the box, and then you have to impose that P is convex. So you have two constraints. F minus P should be non-negativity, should be non-negative on K, on B. So then we know that we can use this positivity certificate, but then you have the convexity constraints, but the convexity constraint is also a positivity constraint that tell you that P is convex on B, the same as this polynomial now, where you have Y transpose the Hessian of P, Y, should be non-negative on B. So you have two positivity constraints where you can use this certificate, the Putinar. Okay? So you would replace those two positivity constraints by what? The first one says that F minus P is non-negative on B, just apply Putinar certificate. And the second one tells you that P is convex on B, so you use the second Putinar certificate, right? And then you have an SDP. And then if you fix D in advance, you get a sequence of polynomial of degree K. Oh, sorry, depending, the K tells you how large you take your certificate, but P is always a polynomial of degree D fixed, right? You fix D, and you look for the best convex underestimator of degree D. Now, the degree of freedom is the K here, how the degree of the psi and the sigma j in your hierarchy. So when you let K grows, for each K you have you obtain a convex underestimator of degree D, and the larger K, the better is your convex underestimator. In conclusion, the moment-SOS hierarchy is a powerful general methodology, and I think it's more powerful than the LP for the reason I have invoked before. Of course, it works for problem of modest size, unless you can use, if you cannot use sparsity in your problem, this is limited to problem of modest size only. And maybe in between you can find, there is a mixed LP SDP hierarchy which takes advantage of both the Putinar certificate and the Krivine Stengel. That would be that now you would represent F like this Stengel certificate, now plus a sum of square. And this is, in combinatorial optimization, this is known as the Sherali-Adams plus SDP hierarchy, because you have this, it's not an LP anymore because you have this SDP, this SOS constraint here. But what is nice is that at least for the easy problem, for a certain class of convex problem, this hierarchy now would be exact. If you don't have this term here, it's impossible to get an exact LP hierarchy for convex problems. Now, if you just add up this sigma 0 fix, and you fix the degree K, so K, here the alpha beta can change, you can make them grow, but you fix the degree of the SOS here. For example, you say, okay, I want sigma 0 to be an SOS of degree 2 or 4, and you fix it. And then you let grow alpha beta. So for all convex problems of degree less than K, where the data are given by convex polynomial of degree less than 2K, this would be exact. So in other words, you would avoid the drawback of the complete LP hierarchy, where for easy problems you cannot be exact, never, except in LP. With this one, at least for easy convex problem, you would be exact. But it would have some other drawbacks also, but I don't have much time to do it. And then I will end up here. Thank you.
Thank you, Jean-Bernard. So we have time for questions. So if you have question, please raise your hand, and so that I can bring you the mic. Questions to Jean-Bernard. Oh, I don't know. Well, he's the closest, so.
Sorry. I have a quick question. So for the easy case of convex problems, what's known about the convergence? Because in the SOS convex, you get it in one step. But if the problem is just convex, is anything known? Or?
You know it's finite all the time, not generically, but you don't know when.
You don't know.
No, there is no bound there, which is a bit disappointing. Yeah. It's finite, that's all.
So a mathematical question and a philosophical question. The mathematical question, are there any results about the speed of convergence in?
Well, no, you know those bounds that without this double tower, which are impractical in terms of efficiency, right?
Right. So
there, I don't know any other
beyond
bounds.
that.
No, I don't know. Beyond that, I don't know. No.
And the philosophical question, so I mean, it's well known, and you mentioned it, that for LP is much more robust as far as size goes.
More robust, you mean?
Yeah, I mean, for large size problems, LP will work much better, whereas SDP will fail.
Well, but on the other hand, you have this binomial coefficients in the terms of the LPR. Another drawback of the LP hierarchy is that you have those bad binomial coefficient that comes into the game when you have this 1 minus g to the power. Let's see, where is it? Sorry. Yeah. When beta is large, you will have those binomial coefficients. So for one constraint of OLP, you would have very small coefficients combined with very high coefficients, and that's very bad. But that's
yeah. So my question was, do you think that the fact that LP works for much larger problem than SDP is just due to the fact that there are commercial LP solvers that have been improved by over 50 years?
That's right. Well, but I'm not very confident that even if you put 50 years of engineers behind an SDP software company, I'm not sure that you would make a big gap into the size of problem you could solve. Because I think that an SDP is much more difficult to solve than an LP.
So you think that there are also inherent issues there? It's not just a question of the fact that LP was smoothed much better.
Yeah, that's right. I think there is a qualitative gap between the LP and the SDP. That's my feeling. Yeah.
Okay, thanks.
For the convex underestimator, so did you try some examples to see whether you can do one thing, compute the convex?
No, because the goal was
just to see what.
We just apply compute convex underestimator because people. So, for example, suppose you have 500 variable problems. Typically, in mix, even if you would have first of all, the SDP, the classical SDP hierarchy cannot apply because it's too big. So, what people would do. They would end up by computing convex underestimator, where each convex underestimator is about very few variables. Your f would be, so you have a f which is a sum of many other f with only 2 or 3 variables, or 4. They rarely go beyond degree 4 and 4 variables. So that's why it is an interesting problem, because you always have to find a convex underestimator of a polynomial of 3, 4, maybe 5 variables. And that you can do it efficiently with hierarchy. And then you make the sum of all convex underestimator, and you replace this convex underestimator by the one they use in the alpha BB method, for example, which is not so nice, but we didn't go beyond that. So it was an example where we could use a hierarchy because the way they compute convex underestimator is for problems with very few variables. They never compute a convex underestimator for a function of 100 variables, because it will be a sum of many polynomials of 3, 4 variables, and they compute a convex underestimator of each function. Might not be the best way to do it, but that's the way they do it. And we wanted to improve a little bit.
Thanks. So one thing about this successive hierarchy is the rate of convergence, but the other thing is the size of the numbers that appear in this approximation. Do you have any idea or any bound of what is...
No. Maybe DD knows more about this, no? But you could have a generic case for which it could be very bad. Maybe.
But for the generic case, do we have any idea what's going on the generic case?
No, really, frankly, I don't know. I don't know any... I don't have any clue about this, actually.
So it may happen that you approximate a small number with big ones, right?
Yeah.
So let's say that the solution is an integer, but then you approximate successively with big rational numbers. So because you don't know, right?
I don't know that. Yeah. This is an open issue. Yeah.
So many thanks, Jean-Bernard, again.
Thank you.